we are going to study the torque on the electric dipole when placed in an electric field. Now, we have here the uniform electric field, and that uniform electric field, that is the E, is uniform electric field. And in a uniform electric field, we have a direct dipole that is minus q and plus q. Let the point where the dipole is placed, it A point, and here it is the B point. A and B is the point where the dipole is placed in a uniform electric field. Now, see, in the positive charge, the force experienced by the positive charge, that is outward, are moving from positive towards the negative, or we can say that along the direction of the electric field. So the force acting here is the FB. That force is along the direction of electric field. That is the force Q into electric field E. Similarly, the force which acts in the negative charge, and that force is towards the positive charge or against the electric field, that force is the F. Here the point B, so we write the FA, that equal to FA. Here we write this FA vector, that is equal to minus Q into E vector. So the two forces are acting on the dipole of FB and FA. These two forces are equal by magnitude and opposite by direction. So it makes the couple of the force. Now the force on the charge, that is B, charge plus Q, is equal to FB, and this is equal to Q into E vector. Similarly, the force on the charge minus Q at point A is the FA, and that is the minus Q into E. By the magnitude, either of the forces are equal. That means in magnitude FB vector is equal to FA vector by magnitude. We know that we have the uniform electric field. Uniform electric field, that means it is constant throughout the space. The value of the electric field, that is the strength, is uniform throughout the space where the dipole is placed. So it is constant or constant. Here the dipole length we consider is the 2A. 2A is the dipole length, that is from this to 2A vector. That is the dipole length. Now, in this particular, the dipole moment from negative to positive, the dipole moment is from negative to positive, that is the P vector, or we can write here the dipole moment. Before that, these two forces are equal and opposite, equal by the magnitude and opposite by the nature. So these two forces, are the net value of the force in the dipole, net value of the force, on the dipole placed in uniform electric field, that F net is equal to FA plus FB. So the net value is the 0, since they have the value that is Q into E vector plus minus of the Q into E vector. So the net value is the 0, or on the dipole the net value of the force is 0. But these two equal and opposite force make a couple, and the couple of the force produces a torque. How? Just see here. If we have something like this, suppose we have a body and two forces are acting by the equal value, that is the Fa, and here it is the Fb, and both the forces are acting on the body. So it will show the linear motion. Linear motion. It is one condition, one case I considered. In place of this body, suppose some linear body is here, and the force acting over this linear body of the same value, so it will produce the linear motion. But suppose the same, by the magnitude the same force, but opposite by the direction will act. Here it is the Fa, and here the Fb is the negative, or we can write that Fb is the negative one. The direction is opposite. So on that case, it start rotating. It start moving, rotational motion. Here it is the linear motion, but in this case, this body whatever here, let it be the body, that body will start moving in a rotational motion, with a rotational motion. So here is the rotational motion. So that means the couple of the force produces the torque, that is the turning effect. This will change. Torque is there, torque is produced here. Torque, and that torque means the turning effect. Torque means turning effect. Turning effect. Due to the couple of the force, or we can say that the torque, that is the turning effect due to the motion of the force, momentum of the force. So that is we come to the conclusion, like or equal by magnitude and opposite by the direction will produce the turning effect. The dipole will move. The dipole will move, that is along this direction and along this direction, and its tendency to align along the electric field direction, and this phenomena is called the torque. So what we come to the conclusion, that whenever the dipole is placed in a uniform electric field, on that case the couple of the force produces the torque, and the dipole will have the tendency to align themselves, align the dipole along the direction of the electric field. So we calculate the torque here, or what we come see what here it is, the net force on the dipole is always 0. Now see the torque, that is the couple of the force produces the torque on the dipole when placed in a uniform electric field. When placed in an uniform electric field. Now what will be the magnitude value of the torque? So torque is the product of either of the force and the perpendicular distance. So torque is the product of see the magnitude here, torque, that is the either the force product of either of the force into perpendicular distance Now that means either of the force. And where is the perpendicular distance? These two forces, when we see this one, here it is the line from this, the force, one force is acting, that is the FB is acting along this direction, along the field direction, and this FA is acting opposite. FA has the direction from this. So the minimum distance between the two forces, that is the NA. NA is the perpendicular distance. Here it is the theta angle, or we can use here also the theta angle. So that is the theta is here. So on that case, AN is the perpendicular distance. So we have either of the force in these two force, that is the FA or FB into perpendicular distance between the two forces, perpendicular distance between the two forces. So we just substitute the value or the relation here. So torque is equal to force in place of this FB into, in place of perpendicular distance, in triangle ABN, the perpendicular distance between the two forces is the AN. So it is the AN. Now we calculate the AN first. This becomes the equation number 1. So in triangle, triangle is what? ABN. And we have the relation sin theta, that is equal to perpendicular by the hypotenuse, that is the AN by hypotenuse is the AB. AB is the length of the dipole. AB is the length of the dipole, that is the 2A. So AN is written as AN is equal to, here it is, AN is equal to, that is AB sin theta, and in place of AB we will write that is the 2A sin theta. So now we use the relation number 2 in equation 1. Here substituting equation 2 in equation 1, we get how much? That is torque is equal to, then in place of FB we will write the Q into E, and in place of AN, that is the 2A sin theta. We know that Q into 2A is that the dipole moment. Since P is equal to, dipole moment is equal to Q into 2A. If we represent in the vector, it is the vector is by the length of the dipole. If that is in vector. But in magnitude, it is the P is equal to Q into 2A. That is in magnitude. So that value will be the torque on the dipole placed in a uniform field. Torque on the dipole turning effect, or have a tendency to align along the direction of the electric field. So here it is the torque, that is equal to, in place of Q into 2A we will write the P, E into P sin theta. But when we write, this is the magnitude value of the torque, that torque produced due to the couple of the force. Couple means that same by the magnitude, or we can say equal by the magnitude and opposite by the direction. So that is the couple of the two forces. Now 3 points we come to know for the two forces. Here what are the 3 points? The force are acting at the two different places, not in the same point. It is opposite direction, second case, and third of the same magnitude. Then only it turned the dipole, it moved the dipole in a field, and then only the two force produces the torque. 3 points for this one torque. Just for the turning effect torque, 3 points is noted. Note point. Note that is for the torque. For torque, that number 1, two forces are opposite and two forces of same magnitude. Two forces of same magnitude. Second point, that two forces are opposite to each other. Opposite to each other. And third point, they act on different point, not in the same point. They act on two different points. They act on 2 points. Then only it produces the torque. It is the condition for the torque. Condition, we can say that condition for the torque. For the torque. Condition for the torque. Here in this 3 points we have that first two forces of same magnitude, opposite in direction, and they act on two different places. Then it is the case for the torque. That means it is the case for turning of the dipole in a uniform field. Or whatever the material, if the force will act in opposite direction and this opposite direction will turn the body along the particular axis. If it has the same magnitude, that means the rotation along the axis. If it is different magnitude, on that case it will act as a helical movement. So that will produce the torque. Now we have the magnitude of the torque, but in vector we write the torque in a vector representation. Torque in vector, that is a sign product or cross product, that is the torque is equal to E vector cross P vector, or we can write P vector cross E vector, or if we use the magnitude as well as the direction, it always acts normal to the, so or in this way we can write the torque is equal to, here it is the PE in place of this sine theta and normal of these two, just like this. The two vector, one is the dipole moment vector P vector, another is the electric field direction. Electric field is constant and the moment from this one we have the theta. On that case the normal direction for this, that is the torque, and torque is the P vector cross E vector. It is normal to that of this one pi by 2. Here it is also normal, that is the pi by 2 or 90 degree or 90 degree. This is the condition for the torque. And if we represent in the vector, first we use the dipole moment vector, then electric field. That is the cross product, or if we write with the magnitude value, P is sine theta to the normal, here it is the magnitude, and this one is the direction. always it acts at on the direction normal to these two vector. That is the case of the cross product. Now, case we will study here. When the torque is maximum and when it is minimum. Now, case 1. For maximum. Maximum, it is the sine value, and sine value like the maximum when theta is equal to 90 degree. That means that electric field is here. These are the electric field, and these are the uniform electric field. And this uniform electric field, there is the torque, there is the dipole, and this dipole is the force acting here FB at the B charge at the A charge, and this is the force here, just opposite direction. This one is the FB and this is the FA. So maximum turning will be here, and that is the maximum torque produced. So for that, theta is equal to 90 degree. For 90, sine of the 90 degree, that is equal to 1. So we have the torque is equal to P into E, or we can write in place of P, E Q into 2A. If we see in the this will give the maximum value of the torque, maximum value of the torque. Now for the minimum value, see here, the torque for minimum, that is case 2. Case 2. Here it is the case 1. Case 1 here, and case 2. If the dipole is along the direction of the electric field, that means if dipole is along the direction of electric field, that means theta is equal to 0 degree. When theta 0, that means sine of the 0 degree is equal to 0. So we have the minimum torque minimum, that is equal to 0. So this is all about the nature of the dipole in a uniform electric field. So few points that to remember, that whenever the dipole is placed in a uniform field, it means dipole will experience a couple of the force. The sense of the couple means the equal by the force having the equal magnitude but opposite in the direction. And that couple of the force will produce the turning effect known as the torque. Or we can say that the rotational motion. If the forces are equal, on that case the motion along the axis. But if the forces are different, let's consider for the non-uniform field, the forces are different, on that case it will move as a helical behavior. So that is the condition when dipole is placed in a uniform electric field. One more thing, the net value of the force on the dipole in a uniform field is 0. So we learn all about this in particular video, in particular class. In the next class, we learn more about the nature of the charge in the field. Okay. Thank you.